Hello everyone, my name is Jianglong. It's my great pleasure to represent my co-authors and introduce our recent work, which is titled Adaptation for Implicit Object Tracking and Shape Reconstruction in the Wild. 3D single object tracking is essential for applications in self-driving and robotic vision. Here, we give the definition of the task. The inputs of the task contain two parts. First is a sequence of point clouds, as the left figure shows. The second is the initial bounding balls, the blue one in the right figure. And our goal is to estimate all poses of the same object in subsequent frames. There are two different paradigms of single object tracking. The first one we call it tracking by detection. The figure below is an example. Given the input point clouds, this paradigm first uses a detector to perform object detection and get an estimated 3D bounding boxes. And then this paradigm uses a tracker to perform association and get the final results. This paradigm mainly focuses on association of bounding boxes, cross frames, and heavily relies on the performance of a detector. So there is no connection between frames in first paradigm. In contrast, the second paradigm aims to leverage historical observation. It leverages the tracking results in previous frames and their temporal connections to the current frame for object tracking. We follow the second paradigm. Next is our motivation. As we can see in the figure, humans can recognize the moving car and aggregate partial information to image the full 3D structure of the car. As a result, by tracking the object over time, we humans can extract better and better shape, which is close to the ground truth point clouds, which in turn helps the tracking. Next, we will introduce our shape representation. Send distance function, SDF, is a widely used shape representation for 3D shape. It maps the spatial coordinates of a point x to its distance to the closest surface. And the deep SDF F is a coordinate-based MLP, which approximates the SDF value. Here is a figure which shows the shape reconstruction with the deep SDF. To perform reconstruction, deep SDF optimizes the shape code by minimizing the difference between the predicted SDF, the green block in the figure, and the observation, the blue block in the figure. Similarly, object pose also can be optimized with the deep SDF. In detail, we first transfer point clouds to object space with the estimated object pose, and then we align the object pose by minimizing the difference between the predicted SDF and observation. Here is our method. Since the initial object pose is provided, we first initialize the object shape code with the aligned point cloud and the deep SDF. And at the frame t, given previous shape code and the incoming point cloud, our goal is to jointly estimate the object pose and adapt the shape. Then we are going to introduce the tracking and the shape adaptation at frame t. We first estimate the object pose with the previous shape and deep SDF. Specifically, we estimate the pose by pushing the point cloud to the zero level side of the SDF field, as shown in the right bottom figure. After estimating the object pose, we use the aligned point cloud to improve the shape quality. We call it shape adaptation. Specifically, we deform the SDF field to match the point cloud, as shown in the figure below. Here is overall pipeline. Basically, at frame T, we first fix the shapecode and estimate the pose, and then we fix the pose and adapt the shapecode. We keep this loop until the end of tracking. Here is our result. First is the visualization result. In this slide, the left top part is our tracking results. The blue box is the predicted bounding box. The left bottom part is our ground truth. The right part shows the process shape evolves. From the video, we can see our method maintains a very high quality of object tracking, and our shape indeed evolves. Here is another example. As we can see, in the evolution, the shape is becoming more and more like GT shape, which in turn helps tracking. Here is the quantitative result. We experiment with both Waymo and Kitty dataset and show significant improvements over the SOTA methods. The first table shows the tracking performance on Waymo dataset. As you can see, we outperform SOT tracker, the first line in the table, by a large margin. Besides, to prove the effectiveness of the online adaptation mechanism, we adapt shape during frames of different lengths. It means we only adapt shape during first n frames, and then we fix the shape code and use this shape code for all subsequent frames. The table 2 shows the reconstruction performance on Waymo. We can conclude from the table 1 and table 2 that the tracking and the reconstruction performance continues to improve as the number of adaptation frames increases.